Thank you very much. So let me get started while you eat. But I'm warning you, soon you will have to do something else besides eat. So the way I'm going to do this is I'm going to give you the answer first, okay? So the answer is that particulate air pollution kills more people each year in the United States than AIDS, breast cancer, and prostate cancer put together, okay? That's the bottom line. The difference is we know how to cure it. We know how to put scrubbers on coal-burning power plants. We know how to retrofit diesel particle filters onto trucks and buses. We know how to improve catalyst efficiency for NOx and hydrocarbons. These are the precursors of particles. We know how to control them. We just don't. And the reason is that people say, well, that would cost a fair amount of money, or we need to phase that in really slowly. So I want you to imagine that we have found a drug that cures breast cancer completely. And that we go and we say to people, well, you know, that would cost a lot of money. So we're going to phase it in. And so, you know, some of you will get it and the rest of you will die. But in, 20 years, everyone will be getting it. So think about what the reaction to that would be. Because that's where we are with particulate air pollution. We know how to get those levels down. Now, that's my part. My talk is over. Now comes your part. Food wasn't that good, right? So, you can do a little bit of work on the side, right? You need to ask me questions so that I can convince you to believe what I just said. Because after all, I may have a lot of publications, but that doesn't mean that everything I say is true. Right? Why should you believe me? I want you to think about that and say, well, what would he have to tell me to convince me of that? All right? And just to get the ball rolling, I'm going to make up one question for you and then start answering it. And then, and then I'm going to start asking you for additional questions. So one question you might ask is, well, what exactly is particulate air pollution, and is there really evidence that more people die when it's higher? So you've heard some description of particulate air pollution. It's little tiny particles or droplets in the air. Okay? But have you ever seen that? Particulate air pollution. Okay, so let me show it to you. This is particulate air pollution. So if you look, see that white stuff there? That's a cloud, okay? But if you look at, see that stuff there? This isn't coming across very well, but this is not a cloud. And you can see also that here it is covering this part of the United States, but not here. See how the land is much clearer here than it is here? This is a particle haze that's covering part of the eastern United States, and you can't make it out under these clouds in the way the colors got translated, but from my computer you can tell that it's also under here as well. But you can clearly see that looks different than that, and it stretches out to sea, and that is the only man-made object that's visible from space. You cannot see the Great Wall of China, it's too thin. But even if the Great Wall of China was wide enough, you would never see it because there's so much particles in the air in China that if I showed you this slide of China, you would vaguely know that there was something down there, but that would be about it. Okay? So that's what particulate air pollution is. It covers the United States with this haze that you can see from space with the naked eye. And what does it do? Well, this is what it does. This is from the Harvard 6-city study. We recruited about 1,500 people each in 6 neighborhoods, actually. We didn't look at entire cities. We pick a neighborhood in each city. And we recruited this cohort back in the 1970s. We measured their lung function. We got their smoking history, high blood pressure, diabetes, all the usual things that are associated with increased risk of dying. We controlled for that. And this is the life expectancy in those cities versus their particle concentrations. This is Steubenville. The life expectancy in Steubenville in the 80s and 90s was 3 years less than the life expectancy in Portage, Wisconsin, after controlling for individual risk factors. That's the effect of particles in the air. Now, to put that in perspective, if we cured cancer in the United States, and I mean all cancer, if we cured all cancer in the United States, life expectancy would increase by about 4 years. Or you could just move out of town to someplace that's cleaner and not have to wait. So this is a big deal. Okay? This is what happened in the London smog episode of 1952. There was a stationary air front over London. The wind velocity dropped suddenly to 0. They had a low inversion layer, and they burned coal to heat their homes. So you now have a city of 8 million people with an inversion layer at 250 feet, trapping all the coal smoke and no wind blowing it out. And so the particle concentration shot up and the deaths shot up. Weather front changed, the particle levels came down, the deaths came down more slowly. Thousands, about 10,000 people died as a result of this episode in a week or so. It's a lot of deaths. Now, those were very high concentrations, and so you may want to ask me about what happens at lower concentrations, or you want to ask me, how this could happen, or how do I know it's not something else, or whatever you want, but it's now your turn. Ask me a question. What do I need to tell you to convince you? Yes, sir.
What's the contribution to cardiovascular disease? What is the contribution of smog or small particulates to cardiovascular disease?
Okay, very good. So what's the contribution of particles to cardiovascular disease? Most of these deaths are from cardiovascular disease, not from lung disease. That's partly because more people die of heart disease in the United States than of lung disease. But most of the deaths are from heart disease. The contribution to cardiovascular deaths, so we include stroke, okay? Cardiovascular deaths are maybe 37% of all deaths in the United States. And if we look at this I would say probably, roughly speaking, right? So this is not a number to quote, but off the top of my head, I'd say maybe 20% of cardiovascular deaths might be associated with air pollution. Yes, ma'am.
What's the contribution to asthma morbidity?
So I'm not talking about that because you had an entire morning of people talking about asthma. So I've published papers on air pollution and asthma, but I want to convince you that it's killing people. Okay, so ask me a question about that. Yes, sir.
How bad are ultrafine particles?
Bad. That bad. Yes, sir.
How does the mortality compare to smokers?
Smoking is worse. I mean, there's nothing like smoking. However, you can not smoke. If you choose to not smoke, you can. If you choose to not breathe the air, you're gonna, in 5 minutes, that's gonna be it. So one of the problems with particulate air pollution is that everybody is exposed and they can't help it. Yes?
How about low-dose exposures, and do the current NACs protect people from?
Okay, so let's talk about low-dose exposures. So we followed up the 6-city study with additional follow-up for mortality. You can trace people through the National Death Index through 2009. So this is from our most recent paper, and we followed these people up through 2009, and we've analyzed it looking at how many people, looking at the risk of dying in each year in that city and what the air pollution level was in each year in that city, okay? And this is the dose-response relationship. This is not a result of my having fit a linear dose-response relationship. This is actually a result of my having fit 32 different dose-response relationships and taking a weighted average of them based roughly on how well they explain the data. Okay, Francesca? So, and it looks linear. And so the old air pollution standard was 15, and you can see it continues all the way down to 8. And what happens after 8, I don't know, because we haven't been able to find a U.S. county with air pollution levels below 8. So we'll just have to see, but certainly stuff happens below 12. So we do have evidence that we still see this at low doses and that current ambient standards are not protective. Here's another example of something at low doses. This is a dose-response relationship looking at the effect of black carbon, which is traffic particles, the black soot that comes out of diesel engines, for example, but some of it comes out of cars as well, and blood pressure. I mean, why are people dying of heart disease? Well, because particles increase their blood pressure. So this was blood pressure at their address. We have a geographic model where we can estimate for everybody in this cohort what the exposure was at their home address. And these people are old. They don't move around that much. It's called the Normative Aging Study, right? And this was, we fit something called a spline, which is basically a polynomial to this data, but again, so it could have been curved, but the data said linear, okay? And so the data dose response looks linear, and this is 1 microgram per cubic meter, half a microgram, a quarter, no matter how low you get. Now, this is not all particles. This is just the carbon particles from cars and trucks and buses. We see an association, more exposure, higher blood pressure. So this is another study that we did where we looked at people who have implanted defibrillators in their body because they're at risk of arrhythmia. And those defibrillators, when something starts to go wrong, they constantly monitor the heart, and they'll administer an electric shock to get your heart back beating with normal sinus rhythm. Okay, so this is looking not at ventricular arrhythmia, but atrial fibrillation, which is a major source of strokes. Okay, and this is looking at the effects of PM2.5, sulfate, and black carbon. And here, the 25th percentile of PM2.5, to the 75th percentile, the range was like 4. For sulfates, it was about less than 2, and for black carbon, it was around a half. And what you can see is 2 hours before atrial fibrillation was detected in these people, particle levels had gone up, and there was an association, an immediate effect of particles, and that persisted looking at longer averaging times, but it happened right away. Okay. We didn't see it with sulfates, and we did see it with the traffic particles at all these different averages, but again, starting 2 hours. So particles, particularly traffic particles, which include ultrafines, but the measure we use is black carbon, are associated with increased risk of arrhythmias happening in these people. And that is very important, again, in explaining why you might have deaths from heart disease and stroke. And again, it's happening at levels way below the standard. I mean, Boston, the average PM2.5 concentration in Boston now is 9 micrograms per cubic meter. We have not been above the ambient standard, the annual standard, ever. And the last time we had a day that exceeded 35 micrograms per cubic meter was 2002. And we've never gotten close since. So these are all happening below the current standard, the entire relationship. Yes, sir?
What's the investment cost per person roughly to make this problem go away in 5 years rather than 20?
Well, so EPA has done a cost-benefit analysis for the transport rule, and the transport rule would result in about a 70% reduction in SOx and a little less in NOx emissions, which are precursors of particles. And, we're talking about not so big numbers. We're talking about, $10 billion, plus some operating costs after that. For retrofitting buses and trucks, large diesel engines, it doesn't make economic sense to do small diesel engines, but, London retrofit 6,000 diesel buses with particle filters in 2 years. And it cost, about $5,000 a bus. So it's not that hard. Back there.
What does that cost translate into to save costs on medical supplies?
The benefits were about 20 times the costs, for that rule. They just can never. There's constant argument over, where the controls have to be put on. And that's because they want to allow trading. If they just said everywhere, then there would no longer be equity arguments, right? Yes, sir.
If you had to choose between you have to choose one of them that you were going to get rid of, which one would you choose out of, I would say, traffic, electricity generation, industrial sources, based on the volume of impact and the potential damage of the types of particles that are released? Which one would be the best one to get rid of?
Probably traffic particles, but that would also be the hardest to get rid of, right? Because, it's not feasible to retrofit cars, right? You just got to wait till the fleet turns over. Bigger sources, it's a lot more feasible to retrofit. So that's the trade. But are you convinced that this many people are dying? I mean, stop asking me about what I ought to do about it. Yes. Oh, well, that's a really good question. Let me see if I can find. So, what we wanted to know was, if we're looking at this cohort, this is the 6-city study again, and we're following them up, if the effects aren't that reversible, then really long-term average exposure would be the best predictor. If the effects were completely reversible, it would be relatively recent exposure. If it's somewhere in the middle, it would be somewhere in the middle. And what it looks to us is the effects are basically in the first 2 years. And after that, they've pretty much gone away. So it looks like the effects are reversible relatively quickly. We have some quasi-experimental evidence to back this up. Arden Pope went back and discovered that in the 1960s there was a strike of the copper smelter workers in the Southwest, where a lot of copper was being produced, generating a huge amount of sulfur dioxide emissions with no controls. The smelters were shut down during the strike. It turned out that the Park Service and the Forest Service was monitoring air pollution even back in the 60s, and he was able to find that in the 4-state area, particle levels dropped by about 2.5 micrograms per cubic meter because of this strike, because these were big sources of the particles. So he looked at what happened to the mortality in those states during the strike compared to before the strike and after the strike, and the same thing in the surrounding states, just in case something weird had happened to happen in that period. So the mortality rates were the same before, during, and after in the surrounding states, but the mortality rates dropped by 2.5% during the strike in the 4 states surrounding these smelters, and went back up after the strike was settled. So that was an 8-month strike. So the answer is most of it is pretty reversible. Yes, sir.
Question, you said you wanted a question to try and convince us.
Yeah.
During that time when those mortality rates went down, what is the proof of the evidence that it was due to the particulates versus potentially injuries or things that were happening in the smelting process?
Oh, it went down. I mean, the number of workers in the smelter was trivial. A 2.5% reduction in, the total number of deaths in 4 states, right? It's not due to less occupational injury by the workers in the smelter. There aren't that many workers. If they all died, it wouldn't have had a 2.5% impact on mortality. Back there?
Okay, location. I had a question about, what if people relocated into a different area? You pointed out that the respiratory is reversible. But you also used an example of temperature inversion, which does happen around here. Would the quality of the geography still, if it doesn't change that
Okay, let me just find one slide here. Oh, I want to find a couple of slides here. So moving, vis-a-vis moving, there's a study in Southern California called, very creatively, the Southern California Children's Study, because they study children. Right, all right. So you're with me. So, but, you know, Californians are a restless lot. They move. And so if they move to someplace else in Southern California, no problem. But what if they move to Minnesota, right? You know, and so they used to say, well, I guess, you know, they dropped out of the study. But one year they got this great idea and they put Ed Aval on a plane. So he got a lot of frequent flyer miles out of this, right? And he flew around to every place where these kids had moved, you know, the previous year, and he measured their lung function. Because what this study was doing was every year they were measuring the lung function of these children to see how it grew and whether it was impacted by air pollution. Answer, yes, right? But this was a different study. This was, okay, compared to the people they left back home, if they moved to a place with lower air pollution, did their lung function grow faster? If they moved to a place with higher air pollution, did their lung function grow slower than the kids who stayed behind? And the answer was yes. So this is, you know, pretty much randomization, right? Some moved to dirtier places, some moved to cleaner places. The places were not chosen on the basis of air pollution. It was, you know, the parents got a job, right? When you move to a cleaner place, your lungs start growing faster if you're a kid. Now, with respect to Pittsburgh, where you've got a lot of hills and valleys, and pollution can build up in there because of inversions, that's absolutely true. I'm just gonna leave it like this. So, you've heard a lot today about what the pollution levels are in the Pittsburgh area based on monitors. Monitors are great, but they only monitor concentrations where the monitor is, right? And there are, you know, 6 of them, so you know it in 6 places, and then you infer about the rest. So there's another way to do it, which is NASA has satellites that are in polar orbit, and they measure particles on every inch of the Earth every day. Okay, so I downloaded that data, which was in, I guess it's still terabytes, it's not petabytes yet, but it's a lot of data, and then you have to calibrate it to turn it into micrograms per cubic meter. And so I plotted it for the mid-Atlantic states here, choosing 2 key cut points. One is above 15 and the other is above 12. Those numbers may be somewhat familiar to you from other discussion today. So the old and the new ambient standard. And this is what the long-term average was between 2000 and 2008. And you can see that not just Pittsburgh, but, you know, Western Pennsylvania, right, is, oh, but what you can't see, that is, these colors change in not nice ways. Let's see if this works. No. All right. Somehow this and this are being put up as the same. But the places that were above 15, there are scattered places and a couple of little squares in New York, but it's basically Pittsburgh and surrounding areas, had an average between 2000 and 2008 everywhere in the region that was above 15, and then every place else in Western Pennsylvania was above 12. Now, obviously, pollution's come down since 2008, but that does show you that you have a serious problem here that, is much worse than in some other locations in the mid-Atlantic. This is one of the highest polluted places because of those inversions trapping things in the hills, as well as the increased number of sources, right? A combination of those. So as long as we are on Pittsburgh, so when we think about causal modeling, we like randomized controlled trials, right? But the reason we like randomized controlled trials is that means that the changes in the exposure, the treatment, if it's a drug trial, right, are uncorrelated with anything else that might affect the outcome, and therefore you can interpret the association as causal. Now, interestingly, that is true at the nanosecond that you conduct randomization and never after that fact, something that some people ignore when they analyze randomized controlled trials, but it is true at that instant, okay? So if we want to analyze data and make it closer to a randomized trial, we'd like to find a way to make our treatment sort of random with respect to other things that might affect the outcome. So one thing we did is we did a study that we published a few years ago where we took people on Medicare and we followed them over time. And we looked at, okay, did they die this year, right? Did they die that year, etc. We knew when they died. And we had air pollution in the cities where they were, including Pittsburgh. And what we looked at is, we said, well, let's take out the mean pollution in Pittsburgh, and let's take out the trend in pollution in Pittsburgh. So if pollution's going down, let me take out that line, and let me now look at year-to-year differences around the line in what the air pollution concentrations are. Right? So that's due to random fluctuations in weather and how strong the winds are and which way they're blowing from and things like that that are unlikely to be killing people, right? And so I've, relatively speaking, randomized my exposure by looking at that. It's not due to the mean, it's not due to the time trend, it's these random fluctuations, and are they related to the mortality rate in each of those follow-up years? Okay, and so we published the overall results, but here are the results for Pittsburgh. Okay, in people in the Medicare population who have had a heart attack, a 10 microgram per cubic meter increase in PM2.5 was associated with an 18% increase in the death rate in that year. And if they had chronic lung disease, it was a 12% increase, and these were statistically significant for Pittsburgh. So that's what's going on right here in River City. And this is what's happening with ozone. It's also true that ozone, these year-to-year fluctuations in ozone, are associated with year-to-year fluctuations in the mortality rate in people who have survived a heart attack and in diabetics. So yes, location matters. And in terms of air pollution, you have a problem in this location. Yes?
Can you talk a little bit about the mechanism that you expect explains that? It's sort of easier to understand how pollution could affect the lungs, but it's sort of harder to understand how it affects cardiovascular.
Great. I've been waiting for this. Mechanism, right? Okay. Okay. So let's see. So one way to deal with mechanism is to look at animal studies, because you can do things to animals that even the IRB in Europe will not let you do to people. And so here's a selection of things that come out of those animal studies. Particles increase blood clot formation acutely. So that might be one way why you might have a higher risk of a heart attack, right? Because you've got increased thrombosis, and that's been demonstrated. Then there were atherosclerosis-prone mice who were exposed to either filtered air or air with particles in it, where during the day it was a peak exposure, and then it came down, and the 6-month average was 15 micrograms per cubic meter. And then they did one of those things that you can't do to people, and they looked at all these arteries, and there was more atherosclerosis in the mice that were breathing the particle-laden air than the filtered air. And again, particles at not such high exposures, and there was increase in oxidized LDL. Pregnant mice were exposed again in this protocol of periodic peaks and then sort of background levels with an average of about 17 micrograms per cubic meter. And then when the mice, the offspring, reached adulthood, they had lower lung function than the offspring of the animals who had been exposed to filtered air. Okay? Longer term exposure also in Hello? Time's up. Longer term exposure was also associated with increased left ventricular hypertrophy.
That one works.
Ah.
Now you're stuck. That one's stuck, yeah. There you go. Not much. I'll go to this one.
That's not connected to the speakers.
Oh, it's not.
Okay. Sorry, whatever I did. So for example, this is the percent of the aorta with plaque in the filtered air mice and the PM exposed mice. And you can see there's about 1/3 more atherosclerosis in the mice getting the particle exposure. Well, that doesn't sound great. And they're getting particle exposure that Pittsburgh exceeds for long-term averages. So that certainly suggests why you might see that. There was another study that looked at the stability of atherosclerotic plaque, and there was, increased foam cells and more recruited cells, etc., in the plaques, and they were less stable when the animals were exposed to particles. Then there was a study looking at dogs, just for variety, I guess. And what they did is they occluded the coronary artery and basically induced a heart attack. And some of the dogs were breathing filtered air, and some were breathing the particles, and they had earlier, higher levels of ischemia and longer lasting levels of ischemia when the animals were breathing particles, which suggests that if you're going to have a heart attack, doing it in a low pollution day would probably increase your chances of making it to the ER room. And if you make it to the ER, you're probably going to be okay at this point, because they'll get you in the cat lab within 15 minutes. We're doing really well with that now. So this is you don't have to slice and dice the animals to do this. This is actually a chemiluminescence assay that detects reactive oxygen species in different tissues in a living animal. And this is cut off on the bottom, but hours of exposure to concentrated particles. So they're like, 100 micrograms per cubic meter, which does happen for hours in the United States. And you can see that within hours, the amount of oxidative stress in the heart and the lung has increased. But again, 100 micrograms is kind of high, so what about lower levels? So they went back to this other study they had done, and they realized, they were looking at something else, but they realized that one of the things they did as part of that was to put the animals in filtered air. So this is comparing animals that have been exposed to Boston ambient air. So in 2000, probably 12, 13 micrograms per cubic meter, and then switched to filtered air. And those are days, 1, 2, 3, 4, 5 days. And over the course of several days, the amount of oxidative stress in the heart and the lung as you go from 13 to 0 drops by like a third, a half. So that's pretty suggestive. And there are some other things, but I wanted to, since you already heard about epigenetics, right? I wanted to point out that these two mice are the same. The difference is that both of them have a mutation that make them fat and give them yellow hair, which is why the color balance is, as I said, not quite right and going through your projector, versus brown hair, and make them obese. They both have that mutation, but this one was, the pregnant mom was given stuff in the diet that helped silence that gene. And that silencing mechanism is epigenetic, which is what you already heard about. And so why am I mentioning it again? It's because air pollution affects epigenetic control of gene expression. So this is a study that looked at people who worked in a foundry in Italy, and they came in on Monday morning after 2 days off, and blood was drawn, and then they worked, and then after 2 days of work, blood was drawn again at the end of the shift, and there was a significant drop in the amount of methylation of inducible nitric oxide synthase, which is induced as a result of endothelial inflammation. So we've also seen since then in non-occupational studies, in the normative aging study, for example, changes in methylation of inflammatory genes, and we've also looked at a pathway analysis. We took the genetic pathway associated with asthma that we got from one of these, standardized sites, and we showed that both black carbon and sulfate were associated with changes in the methylation pattern in the asthma pathway. So we do see things that might universally affect the body in a lot of different systems, which is interesting because one of the things you haven't heard about yet, but you now are about to, is there's growing evidence that particles affect cognitive function. So we found that particles were associated with lower IQ in children when we computed lifetime exposure at their address and tracked their moves. In adults, in the nurses' health study, we also found that exposure at the address was associated with a faster rate of cognitive decline in the participants who were all over 60. And there is also, again, toxicologic data to support this. So there's other stuff going on. Yes, sir?
What about psychological effects?
Ah, that's very interesting. It turns out the normative aging study has a lot of psychosocial tests. There's the lifetime optimism test, the brief symptom inventory, Minnesota multiphasic inventory. We have a bunch of tests, and we're actually now looking at the association between air pollution and people's scores on those tests. And since we haven't published it yet, I think that's all I can say. But I think it's a very interesting place to go. Yes, sir.
Is it greater health hazard, indoor or outdoor pollution? And if indoor pollution is a hazard, what measures can be taken to reduce that?
So in the United States, outdoor pollution is a bigger hazard. In India, indoor pollution is a bigger hazard. So it depends on where you live, because we don't cook with biomass stoves, right? And we, unlike the Brits in 1952, don't heat our homes with coal fireplaces, right? We burn gas and we use electricity. And so indoor sources of pollution are smoking, right? Which you shouldn't smoke, right? But leaving that aside, other than smoking, there's, cooking, right? I mean, so you throw the stuff in the frying pan. I did that once, and I had a dust track. I had this portable, continuous particle monitor in my kitchen, and let me tell you, making schnitzel is a life-threatening event, and that's before you eat it. But you don't cook for that many hours of the day, right? So the long-term exposure in this country, in general, except in some isolated populations, is from the outdoor stuff. In developing countries, indoor sources are really a major problem. Yes, sir.
I was wondering what you think could be done to get more awareness or convince more of the clinical community. The clinicians don't seem to talk about this aspect of our health very much. Or do you feel like that they are convinced of it and that there's some other issues going on? But I'm curious, what do you think it would take to convince more of the clinicians?
So someone once asked Heisenberg, how did you convince all these old-fashioned classical physicists to believe in quantum mechanics? And he said, I waited for them to die. So, to take a slightly more optimistic view, right? The American Heart Association published in Circulation, 2 years ago, a position statement on particulate air pollution, right, which was pretty strong, and went into a lot of detail. So if cardiologists read that, then they would have the information. And actually, the group that publishes clinical guidelines for cardiovascular disease just, I think last year, came out with updated guidelines which now include a mention of air pollution and say, well, particulate air pollution can cause this and that and that, and so, now they didn't recommend any particular treatment for that, which, is a little beyond a cardiologist's ability, but at least it's raising the awareness, I think. And so I think we just need to keep doing that. It's like anything else. People have to get used to an idea. And for people to get used to an idea, they need to be exposed to it multiple times in multiple ways until they start going, oh, yeah.
Are there studies that are controlled for nutrition and exercise? Because I think that's kind of what most clinicians commonly think, like, oh, well, we have heart disease in Pittsburgh because of what people eat and because we don't exercise.
Okay, so we have diet and exercise in the normative aging study, and so we are able to control for that, but that's looking at more of these short-term effects. So thinking about the chronic studies, these cohort studies on long-term mortality, I believe that they did that in the American Cancer Society study. I think they had that information. We did not in the Six City study. The Nurses' Health Study, right, was invented to collect that information. And so the Nurses' Health Study does control for that, and they've reported association between long-term survival and PM 2.5, as well as cognitive decline. Yes?
Can you elaborate a little on the differential impacts on different subpopulations, either people who do have chronic diseases or who might have exposures to other risk factors?
Sure. So of course, there's a short-term effects and long-term effects. There have been fewer studies looking at effect modification for these long-term survival things. But in those, they find people with lower education levels or lower socioeconomic status tend to be more at risk. In the acute or subchronic studies, we see higher risk in people with more psychosocial stress. We've reported that, and others have. There's also evidence of higher risk in people who have diabetes for some of these outcomes, not for all of them. Atrial fibrillation is showing up as something that's an effect modifier in some studies, like acute mortality studies. We've seen that. And there is some data on race, but not enough. And that's partly because, the Six City study and the ACS study, which were the first cohorts, and the nurses, right, don't have that many blacks. And so that's a problem, which is hopefully being addressed in some of these other NIH cohorts that do.
I have another question. Given that we know that, we can reduce exposure, but for whatever reason we're not able to do that politically or for other reasons.
Oh, we know the reason.
But given that that's the landscape in which this problem is situated, what are the other kinds of steps that we might consider taking to protect people from exposure? So what are the best ways for individuals to think about protecting themselves or communities thinking about reducing the exposure of their population?
I don't think that people should have to walk around their entire life wearing an N95 mask. But it works. So this was a paper that was published a few years back where, 100 people were recruited and they walked the same route in Beijing where the air quality index today is 249 right now, this hour, where 100 is the ambient standard. Okay? So it's polluted, You can get an app. This is actually a Chinese app, by the way. You know, the people in China are actually interested in this. The other interesting thing about this app is that in every city that has a U.S. embassy or consulate, they take the particle data from there rather than from the government monitors. Their choice, you know, what can I say? So these 100 people walked around on a route for an hour in Beijing, once wearing a particle filtering mask and once not. And their blood pressure was 3 millimeters lower when they were wearing the mask, and they had less ST segment depression. So filtering does work. HEPA filters potentially can work. However, if there's a lot of air circulation in and out of the house, right, that's not going to be so effective. So, I mean, like, if you put a HEPA filter in your bedroom and close the door and the windows, right, that'll get the particle levels down for sure, right? If it's a nice spring day and you open the windows, you know, it's going to be more of a challenge for this filter to keep up with the air circulation. It'll get down some, but it won't do nearly as good a job. But there are HEPA air cleaners available, and that's something people can do. But if everybody in the United States bought a HEPA filter, that would be more money than it costs to put scrubbers on coal-burning power plants. I mean, that's ridiculous. And then you got to remember to change the filter or it stops working. Most people buy these things, they plug them in, and that's the last time they look at them. That sort of reduces effectiveness. I'm getting the idea that it might be time to finish. But
Is there any evidence that outdoor air particles coming into an indoor compressed environment increase both in terms of health effects or intensity?
no, outdoor particle. There's particles in this room from outdoor, and given the kind of building this is, they're probably at about 40% of the concentration outdoors, because this kind of building has a low air circulation rate compared to a home. Most commercial buildings do. And so there's a lot of actually filtration by the building envelope. Now, if you're in a building with open windows and stuff like that, then you get it up to about 80% of the concentration outdoors. But it doesn't actually get concentrated unless you try to deliberately do that. You know, if you sucked in air from the outside and tried to concentrate it. But normally it's less than outdoors. Okay, thank you very much.
I tried to catch it, but I couldn't. I apologize. I want to thank Dr. Schwartz for that excellent interaction he did. We're actually going to take about a 10 to 15 minute break, so you can visit the exhibits and network and take a break if you need to. And then we'll reconvene at 1 o'clock right next door. And we're actually going to be moving into the other health effects of air pollution other than asthma. That's what we're going to concentrate on all afternoon. And then following those presentations, we're trying to have a 30 to 45 minute panel discussion depending on time. So we really appreciate all your participation this last hour, and we look forward to it later on. So we'll see you in about 15 minutes next door.
A couple of minutes.